Screencast number 1 for Chapter 6 in AP Physics. It's going to be about momentum and impulse, as you can see by the title. And then we're going to look at collisions. You can see practical applications of this all over the place. This will help us to answer all kinds of questions, such as what happens during a collision between cars, how can we reduce the damage that might be done, especially to the occupants in the car and perhaps to the car itself. We're always interested in reducing serious injury, of course. How do rockets work, flying and going through space? This will help us to answer that question. Animals involve momentum in lots of different ways, as you will see. And then, of course, in sports, there's an awful lot about sports that involves momentum and impulse and collisions between a racket or a bat or a golf club and a ball. So we're going to be addressing these kinds of illustrations as we go through this chapter. A couple things here in the yellow print. The more momentum an object has, I'm reading right here, the more force has to be applied to stop it in a given time. And that should be kind of intuitive. Your textbook uses this term metaphorical. We just have a sense, an intuitive sense, that if something has an awful lot of momentum, maybe because it has a lot of mass, or because maybe it has an awful lot of speed, we feel like it has this thing called momentum. We have a gut sense of what that momentum is, and it's going to require more force to stop that or reduce the momentum of that object. And that force might reduce the momentum by reducing the mass, or it might reduce the momentum by reducing the speed. So we have a sense that this momentum, and I'm going to abbreviate the word momentum, seems to depend upon what the object's mass is, and the momentum seems to be proportional to what the object's speed is. And you'll see that in just a minute. In fact, that's exactly how we define momentum. Momentum is defined as mass times velocity. Velocity, of course, is a vector, so therefore momentum is going to be a vector. Now we use the letter P to stand for, to stand for momentum, because the letter M is used for too many other things, especially mass. And it might be, and I'm not sure this is the case, but later on when we see the word impulse, maybe the letter P comes from the word impulse, because impulse is related to momentum. That's just a hypothesis on my part. And we can talk about momentum of an object if it's moving in a certain direction. And this is my y-axis and this is my x-axis. We can find the momentum in the x direction and the momentum in the y direction by resolving the momentum vector. And so we can talk about the momentum in the x and the momentum in the y. Now, the magnitude of the momentum can be related to its kinetic energy. Remember, kinetic energy also has mass and velocity in it. The kinetic energy is 1/2 mass times velocity squared. So, for example, if we take this equation right here, and we say that momentum is going to be mass times velocity. Mass squared times velocity squared is momentum squared, divided by 2m. And you can see that this mass cancels out one of the two masses up here, and we get 1/2 mv squared. So kinetic energy equals 1/2 mv squared, which therefore means it equals momentum squared divided by 2 times the mass. Now, another thing about momentum, we know for Newton's second law that force equals mass times acceleration, and acceleration is velocity divided by time. And so mass times velocity is momentum, that's the P, and there's my change in time. So the force is going to cause a change in momentum over a time interval, over a change in time. Another thing we can say, and I'm reading right here, the change in an object's momentum divided by the elapsed time equals the constant net force acting on the object. And in fact, it doesn't have to be the same force all the way through. We can talk about a momentum, and for some reason this is erasing again. Even when the forces are not constant, we can make this observation that the change in momentum divided by the change in time equals the net force that's going to act on the object to produce that change in momentum in that interval of time. Now, if we go back to F equals ma, and instead of acceleration, we have our velocity over time, change in velocity over time. And then we multiply both sides of the equation by time. We get force times time equals mass times the change in velocity. And of course, mass times the change in velocity is my momentum. We have this force times time on the other side, and that is known as the impulse. The impulse, force times time, is what's going to cause my change in momentum. So impulse equals my change in momentum, my change in P, my final momentum minus my initial momentum. And again, the force on an object is rarely constant. If you think about hitting a baseball with a baseball bat, at the very first contact, the baseball comes into contact with the bat. The baseball becomes slightly compressed, but as it keeps moving, it becomes more and more squashed together, and then it's going to rebound off the bat until the moment that it loses contact with the bat. So the force gets greater and greater, and then the force gets less and less. This is first contact right there, and this is when the ball leaves the bat right there. So we would want to find what is my average force, and how can we find that average force? Well, we can come over here and we can do it in a number of ways. The first way, of course, would be to find the integral of the force as it goes from T initial to T final, the integral of that force over that dt, that small change in time. So if we had that equation for the line, we would plug it in right there, and we could integrate that to find the area under the curve. And another thing we could do, like was done in the last chapter, is if we had graph paper, we could find out how many boxes are inside this graph. Another thing that we could do, and I'm going to erase all of that, is we could make rectangles. Could have a rectangle here and another rectangle there and another rectangle there, and add up the area of all of the different rectangles to approximate the area under the curve. And again, you'll notice that there'll be some area within each rectangle that does not fit underneath the curve, and there might be some places like right there where there's some area under the curve that's not in one of my rectangles. And we would hope that as we make my rectangle skinnier and skinnier, in other words, this would be the limit as my change in T approaches 0, we can get a better and better approximation of the area under the curve. Here's another way that we could do it, and I'm going to erase what I just did. And what we could do is, if I took out a piece of paper and cut it, maybe trace this and cut it, and took that piece of paper that I cut that looks just like this curve and find its mass, then I could take another piece of paper and make it a rectangle and keep trimming it until its mass of the paper equals the mass under here. Well, this rectangle, it's easy to find the area. It's just going to be the force times the time, or we could say the height times the length. And so knowing the area under the curve, which is going to be my change in momentum or my total impulse, either one, because impulse equals the change in momentum, where impulse is force times time. Once I know the area of my rectangle and I know its mass, I can find the area under this curve because its mass is going to be the same. That's another way to do it, probably not the way that you're going to do it. And let me try to erase all my marks. But the idea is, if I can find a rectangle with the same area that I have under the curve, then I can measure this area under the curve, which is the integral of my force times my time times some kind of constant. All right, let's take a look at this picture right here. This is a micro flash, which means that we are opening the shutter a third of a millionth of a second. 0.33 is a third of a microsecond. And if we can capture the picture there, you can see the bullet right there. It entered this side, went through the bullet, and here's some of the debris of the apple coming out. Here's the debris of the apple on the other side coming out, and there's the bullet. And we can use stroboscope, which is very, very fast flashing light. So in the brief interval that the light flashes, and the exposure time is a third of a millionth of a second, we can capture the effect of the bullet on the apple and the path of the flight of the bullet through that apple. And we can study an awful lot of collisions like this and talk about the momentum of the bullet. There's a lot of those kinds of pictures online. Maybe you watch boxing. I find it a rather difficult sport to watch. The idea of trying to hit somebody else as hard as you can, especially in the head, does not seem to me like it ought to be a good sport. But a good boxer is going to roll with the punch. In other words, they're going to try to be moving their head back as the punch comes their way. And of course, what that does, it's going to increase the amount of time that the punch is going to be delivered, which reduces the force. If you just stand there and take the punch, you're going to get a big force in a very short amount of time that the punch is landing on the head. And of course, the greater the force to the head, the more damage can be done to the head, especially the brain. And in God's providence, we have this fluid that encompasses the brain to help to absorb some of that impact. Now you can see right off the bat that that's the whole purpose of an airbag in a car, to inflate and maximize the time that your head moving forward comes in contact, not with the dashboard, not with the steering wheel, but with the air in the bag. And that's going to reduce the amount of force of impact, because the momentum of the head, which is going to be the mass of the head times the velocity of the head forward, is going to be constant. And you'd much rather have it look like this than to look like this. This is what you don't want. So we try to reduce the amount of force by increasing the amount of time that the head is in contact with whatever the object is that's stopping it. So if we take a look at this golf club, here's this golf club right here. Looks like a driver by its shape, and it's in contact with a golf ball. The golf ball has a certain mass, and we're going to assume that the ball leaves the club face at a speed of 44 meters per second. So you'd have to have some way of measuring that. And we're supposed to find the magnitude of the impulse in part A, and then estimate the duration of the collision and the average force. That would be the T and the F. We're given one other piece of information, that the golf ball is about 2 centimeters, or at least the distance the ball travels on the face of the club. So when we come over here, we see that my impulse is going to cause my change in momentum. And my change in momentum is going to go from maximum to 0. So my change in momentum is going to be 2.2 kilograms per meter per second. Notice the units for momentum are the same as the units for impulse. And no, we do not have a special name for kilogram meters per second. It's not named after any famous physicist. Maybe someday that might be your last name, perhaps. So 2 points again. The units of kilograms times meters per second are the same for impulse as they are for momentum. And point number 2, there is no special name for kilogram meters per second. Like the Newton is a special name for a kilogram meter per second squared. Now, once we have that, we can find the time of impact. And so if you remember that velocity equals distance divided by time, therefore time equals distance divided by velocity. And so if the golf ball travels a distance of 2 times 10 to the minus 2 meters, which is 2 centimeters, like was said earlier in the problem, and the speed is 22 meters per second, we see that the ball is in contact with the club of the golf, with the face of the golf club, 9.1 ten-thousandths of a second. And so now when we go to find the force, remembering that force times time equals my change in momentum, we solve this for my force. And so we put the change in momentum in the numerator right there, and the change in time in the denominator, and we get a force of 2,400 newtons. Now down here they talk about the importance of following through, as well as the importance of shifting your weight of your body from your back foot to your front foot in order to increase the total amount of momentum that the golf ball is going to have. And I'm not a golfer, so I'll take their word for it. That sport was always too expensive for me. Here's another example about bumpers. And in a crash test, we're given the mass of a car, 1.5 metric tons, and we have the initial and final velocities of the car, and this is very important. One of the velocities has to be negative because the direction of the car is changing. So if we decide going to the left is negative, that means going to the right is positive. And so when we go to find our change in momentum down here, here is my initial momentum, here is my final momentum, and again, notice that one of them is negative. So when we find my change in momentum, we are subtracting a negative, which requires me to add them up. So when something rebounds, we get much more momentum than if it didn't rebound at all. In other words, if you throw a rubber ball at a wall and it bounces back, you're going to get much more momentum than if you throw a clay ball at a surface and the clay sort of sticks to the surface or just plops on the surface and then drops. You get a lot more momentum, which, by the way, is one of the reasons we do not want to have rubber bumpers, because you would bounce back so fast that your change in momentum would be very, very large. And you don't want a change in momentum very, very large, because that would cause whiplash to the people inside the car. And you hate it when that happens. We can also find my total force then is going to be the change in momentum. And again, the greater the change in momentum, the greater is going to be the force experienced by the car and the occupants in the car. Hopefully, you would maximize the denominator, make the denominator really, really big by having an airbag to at least absorb the amount of impact for the occupants. The car, not so much. We want to design the car, by the way, with collapsible fenders and bumpers and trunk, the front of the car, the hood, so that by maximizing delta T, we minimize the force that even the car experiences, which is a benefit to the occupants as well. And so here's a discussion which we're not going to take time for, talking about injury in automobiles and giving you some real-time data, some actual data of the kinds of numbers if you were to measure the impulse and the change in momentum for an individual. So instead of getting a really nice curve like this, the actual curve would be very, very irregular as metal crumples and things like that. And if you're doing accident reconstruction, or you're working on engineering better designs for cars, or if you're a physician studying the effect of collisions on people in the car and trying to figure out how to better protect them, you would want all that kind of information, which is why we use airbags, which increases the collision time. You want your head going into an airbag that slowly collapses and absorbs your energy, your momentum going forward. You don't want the head to be bouncing off the steering column or the dashboard. It makes a big difference. We deploy accelerometers when we study this, and you've already used an accelerometer in one of your labs. And the way that we inflate this bag very, very quickly is the accelerometer, when it senses a sudden change in acceleration from stopping, it sends a signal to ignite a blank explosive charge that fills your airbag with gas very quickly. And how do we store that electrical charge so we have instant ability to ignite the tank that's going to inflate the bag? We use a capacitor, which we'll talk more about when we get to chapter 16 in your text on electricity. And maybe you've heard in the news about some defective airbags by a company that used to make an awful lot of airbags, because the explosion that produced a rapidly inflating bag also produced some shrapnel from some of the pieces that exploded, and those damaged the patients as much as the collision without a bag might have damaged the patient, the occupant of the car. And it says that because of the airbag, it reduces the effect by 1 order of magnitude. 1 order of magnitude means by a factor of 10 times. And so instead of maybe going from 10 to the 4th, maybe it's 10 to the 3rd Newton per meter squared, or 10 to the 5th, depending on which direction you're comparing. That would be a factor of 10. Now, one of the most important concepts in physics is the conservation of momentum. And this is the idea that momentum is always conserved in a collision. Momentum is always conserved. Kinetic energy is not always conserved, because you often lose in a collision energy due to heat. Energy itself would be conserved if you're able to incorporate or include the amount of heat that is lost in a collision. But momentum is always conserved. And we'll be doing some problems in screencast number 2 that will show this. Now, at the microscopic level, it's very hard to discuss collisions because on a sub-microscopic scale, we're starting to look at the movement of individual particles and molecules, and we're looking at the electrostatic interactions between positive and negative charges on the surface of things. But even at that level, at some point, if we were able to measure it, we would talk about momentum being conserved. And the point is that even at the microscopic level, your charged particles may not be touching each other. So what a collision actually is at the microscopic level is when the two particles that are super, super small come in contact. By contact, I mean they get close enough to repel or attract each other. And therefore, there is an interaction that doesn't necessarily involve contact, but does change the trajectory of those particles, and therefore there is a transfer of momentum. So we can talk about the momentum of subatomic particles, like ions and atoms and protons and electrons and nuclei. In the picture over here, we have a larger mass and a smaller mass colliding, moving together, and when they get close enough to interact, not necessarily touch, but to move apart, and this is a small letter M here, not a negative sign. Let's say they both have the same charge, and so they repel each other. And let's say we have a proton, so this would have a positive charge, and this would be a helium nucleus, which has 2 protons, so this would be 2 positive charge. It's interesting that suddenly came out purple. In any case, it has twice the positive charge. They're going to repel each other, and therefore, down here, this velocity, v1, is going to be 2 times v2. Because it has half the mass, it's going to have twice the velocity. But the velocity is going to be negative because it's moving in the opposite direction. Don't forget that. There is a problem on the test over this chapter where students frequently forget the negative sign because an object is rebounding. And so if we look at the total momentum of one object during the course of its collision, and then the total momentum of the other object that it collided with, and again, collision does not necessarily mean contact, the area under both graphs should equal each other because the area under the graph is momentum. And here's an example of a squid that often propels itself by squirting water out one end, so it moves in the other end. Or you can think of a rocket moving through space. As it shoots its gases out one end, the rocket goes in the other end. Of course, the mass of the gases is very, very small, and the velocity of the gases is huge, being ejected from the combustion chamber in the back of the rocket. And the rocket itself is going to have a huge mass, and so its velocity is going to be very, very small. But again, the momentum this way towards the left equals the momentum towards the right. So a rocket can go through space. In a sense, the rocket is pushing off of the gases that it's expelling. So the law of conservation of momentum simply says if we add up the momentum we start with from one or two objects, it's going to be equal to the momentum that we have for those objects afterwards. A lot of times one of your objects might be stationary. If one of the objects is stationary, let's say object number 2 is stationary, then its momentum would be 0 because its velocity would be 0. And this explains why when you see somebody jump into the air, you might say, well, where's the conservation of momentum? Well, the cheerleader, in this case, or somebody who's jumping, would have a very, very, very small mass, and their motion compared to the Earth would be very, very great. Meanwhile, those of you who are still awake at this point in screencast would know that the mass of the Earth is much, much bigger than the mass of the cheerleader. So therefore, the velocity of the Earth in the opposite direction would be minuscule, extremely small. But again, momentum would be conserved. And it would be interesting, and I've done this calculation, to imagine if everybody on the planet got in the same place, shoulder to shoulder, and jumped, what impact would that have on the movement of the Earth? The word recoil, again, let's imagine that you throw on a skating rink, an ice rink, and you throw a baseball or you throw your physics book in one direction, you're going to go in the other direction. Or let's imagine you shoot a gun and the bullet goes in one direction and you're going to go in the other direction. You're going to recoil. But again, the momentum is going to be constant. The mass of the bullet, for example, times the velocity of the bullet is very great, and your recoil, you have greater mass than the bullet, a bigger mass, but your velocity is going to be a lot smaller. The first time my oldest son, who's now a sniper-trained SWAT officer, fired a rifle way back in high school, he had experienced firsthand the recoil of the rifle. And the rifle had a scope, and the scope was up against his eye, and he got a bit of a black eye from the recoil of the scope against his eye as he fired the gun. And now he knows better. Now we're going to look at a problem with an archer. The archer is going to be on frictionless ice, if there is such a thing. And then the archer is going to shoot an arrow, first horizontally to the earth, and then at an angle of 30 degrees against the earth. And we use this data to solve 3 different problems. Now, if you can't see the archer there, it's because the archer is camouflaged. So I made an arrow so you can see the archer. Now, the first part of the problem is we want to find the archer's velocity moving to the left when he shoots an arrow towards the right. And so we have the momentum of the archer plus the momentum of the arrow, and they have to equal 0. The reason they can equal 0 is because V1, the velocity of the archer, is going to be to the left, and V2, the velocity of the arrow, is going to be to the right. And this problem is assuming to the right is positive and to the left is negative. And so we find that the velocity of the archer is this value right here. Now, let's say that while the archer is still moving to the left, and that's an easy thing to overlook in this problem. So we move to part B. While the archer is still moving to the left, the archer is going to fire another rifle. So the archer is going to have a certain amount of momentum to begin with, and the other arrow is long gone. And then the archer is going to shoot another arrow, and that means that the archer's mass is going to go down by the mass of one arrow that's in the little bag in the back where the archer has all of his arrows. And that mass of that arrow is going to be going at a certain velocity at a 30-degree angle. So we're going to have to find this component right here. And that's going to be the final velocity times cosine theta. And that part is right here. So when we solve this equation for what I highlighted in green right there, when we solve this equation for the velocity of the archer, after the archer fires the second arrow, we get a rather complicated equation that looks like this when we solve the above equation for the final velocity of the archer. The archer is V1. We plug our numbers in. We see that the archer now has this speed. Notice that the original speed of the archer from firing or shooting the first arrow has increased, because now the archer has fired a second arrow. And indeed, the archer could keep firing arrows until he's out of arrows and keep going faster and faster. Now, to estimate the average normal force acting on the archer as the arrow is accelerated, you might recall this kinematic equation from a few chapters ago. We can solve this equation for A to find the velocity of the arrow. And then we can find the time that the arrow is in contact with the bowstring of the bow. And that is by taking, if we know that acceleration equals velocity divided by time, therefore time is going to be the velocity over the acceleration. And here's my change in velocity from speed of 0 up to 50 meters per second. And here is my acceleration, which is down there. And now we can find the time that the arrow is connected to the bowstring of the bow. And finally then, we can find the force. Now here we're going to have to keep in mind that when we do our vector diagrams, the normal force, which we're asked to find, is F sub n, perpendicular to the surface upwards. And we have our force of weight acting down, but we also have the downward component. We were already looking at the horizontal components of momentum, but now we have a downward and upward component. There's going to be the upward component because we're firing the arrow into the air, and so there's going to be the pushback downward here, which is going to affect my normal force. And so that's where we get this equation right here. This, they're calling the F sub r, which is going to be the force of, it's supposed to tell me, right? That's right, it's the reaction force, the equal and opposite reaction force. So if you're shooting it up, the equal and opposite reaction force is going to shoot down, and that's going to reduce my normal force from being just the weight of the archer and arrow. And so now we can solve for that normal force right here. So we're going to stop right there, but I encourage you to do the quick quiz before you close out this screencast.